wait for a couple of minutes and let's see if people join. Otherwise, I will start the session after a few minutes. Okay, let's start the session. Okay. I hope that I am audible and my screen is visible. So, hello everyone, welcome to the live session for the course Introduction to Semiconductor Devices. So, this is week 9. We have 3 more classes. So, let me introduce myself first. I am Ananya. I am a PhD student in the Department of Electrical Engineering, IIT Kanpur. I will be the TA for the session, and as always I will start the session with a brief overview of the topics those were discussed in this week. So what we have learned in this week 9, and we are discussing about MOSFET this week. Okay, we already have the background knowledge for that. We have discussed about PN junction, we have discussed about MOS capacitor. So we already know, familiar with some basic equations, how the current conduction happen, how the inversion happens. All this things we have already learned, and today we will discuss about MOSFET, which is the basic like fundamental block for like most of the circuits, and basically MOSFET dominates the silicon VLSI industry. Okay? So actually in circuits we use transistors. What are transistors? Transistors can act as a switch and act as an amplifier. Okay. So we know that there are two types of transistors, BJT and MOSFET. So BJT will not be covered in details in this course. If you are interested, you can learn. BJT is basically like this 2 PN junction, okay, and the basic PN junction operation and the current conduction, how it happens, all those things will be still valid there, but because of the device configuration, few things will be different, but it is not that difficult to learn just by reading the textbooks. Okay, so why we need transistors? As I mentioned earlier, that insulators never conducts current and metals always conducts current, and we wanted something in between where we can control the current conduction and how it conducts as per our need. Okay, so semiconductors are useful in that way, and using semiconductors, people have developed these transistors which can act as a switch, whether we want to transmit current, whether we want the device to be on or off, that we have that control, or we can amplify the current or voltage, like we have the control of how much amplification we want. Okay, so there are two types of transistors, BJT and MOSFETs. Actually, BJT and field effect transistors. There are different types of field effect transistors. We will only discuss about MOSFET in this course. So there are few fundamental differences between BJT and MOSFETs. If you are interested, you can learn about it. So like there are certain applications where MOSFETs are more useful. Okay. Many times switching application people prefer MOSFET, and in circuits like where we need low power consumptions, MOSFETs are useful because we know that in CMOS technology the power consumption is less. Okay, if we want to design a circuit with transistors, we can use BJT or we can use MOSFETs, but if we use MOSFET, especially using CMOS technology, then the power consumption will be less. Okay, that is the main advantage, and that is why the MOSFET technology has improved so much over the years. Okay? BJTs are of two types, either NPN or PNP, and similarly MOSFETs are of two types again, NMOS or PMOS. As we discussed in MOS capacitor, NMOS has a p-type silicon substrate and PMOS has a n-type silicon substrate. Why it is still called NMOS? Because the channel, the inversion layer that is formed, that is of type electron, that consists of electrons. That is why this is known as NMOS and this is PMOS. So how the device look, how it is different from MOS capacitor. So in MOSFET we have 4 terminals. In MOS capacitor we have 2 terminals, so one at the metal, one at the semiconductor side. Okay, so this is a configuration of like the device structure of a MOSFET. So it has either p-type silicon substrate or n-type silicon substrate, and this region is known as body region. Okay, this may not be the whole wafer. We can have like a small area where it is a p-type silicon substrate, which is like the body of our transistor. Okay, body of our MOSFET. So that is why this is known as the body terminal. We can have applied voltage to this terminal also, this is bulk or body, and we have these two regions which are highly doped if it is a NMOS, and we have a p-type silicon substrates, then these are N plus doped. Okay, and these are known as source and drain. These are identical from fabrication point of view. Depending on which terminal we are applying our voltage, based on that we define whether it is a drain terminal or a source terminal. This is our oxide layer. This oxide earlier was silicon dioxide. Now as we discussed earlier sessions, that we are moving towards high K dielectric, so that there is no tunneling between the channel and the metal layer. Okay, even if we make our devices very small, very thin, there will be no tunneling if we use high K dielectric, like we did one problem last time. So one example of high K dielectric is hafnium dioxide. There are other materials also, I'm not very sure about it, but we mostly discuss in terms of silicon dioxide. Okay, and then this is our metal terminal, which is our gate. Okay, we know that metal is also, now we don't have like a proper metal, we have polysilicon that kind of behaves like a metal. These are highly doped silicon. Okay, so we have this four terminals. Most of the times we keep the source and body terminal, like we connect it, we short it, and we often apply a low, either we apply a 0 volt to the source and the bulb, I mean the relative potential I'm talking about, or we apply the bias in such a way that this N plus and P junction is reverse bias. Okay, we want our channel to form here, and we want our gate to control that channel. Okay, we don't want any extra current conduction between these P N junctions. Okay, N plus P and N plus P, these two junctions. Okay, that is why the bulk or body terminal is biased in such a way that these two junctions are always in reverse bias. Now in MOSFETs we have again two types of MOSFETs: enhancement mode and depletion mode. In enhancement mode, what happens? If you remember the threshold voltage expression for MOS capacitor, which is also valid for MOSFET, is that Vt equal to V flat band voltage minus Q depletion by COX plus 2 phi f. Okay, the signs are as per whether it is NMOS and PMOS. Okay, we know that QD depletion charge is QNA into W, which is negative for NMOS, so overall this term will be positive, and similarly it will be, the sign will be opposite for PMOS. Okay, so basically if our flat band voltage is 0, we get Vt greater than 0 for NMOS. If my flat band voltage is 0, or the value is such that we get overall like threshold voltage is greater than 0, or it can be less than 0 also if we have like a large negative flat band voltage. Okay, so what happens in enhancement mode? The channel is not formed when gate bias is 0. Okay, as soon as we apply a voltage which is more than the threshold voltage, then the channel will be formed, and based on the biasing condition between source and drain, we will get a current. Okay, so we use the gate terminal to control the channel and hence the current conduction. Okay, we create a channel which is basically the inversion layer. Okay, and use gate voltage. To control the current. Through the channel. Depletion mode is slightly bit different. We have discussed about flat band voltage. If the bands are not flat, ideal if the Fermi levels are not equal in the metal and semiconductor side, or if there are interface charges and other fixed charges are present in the oxide layer, then there will be a band bending even before applying the gate bias. Okay, now if our flat band voltage is such that the band bending is such that the inversion layer is already formed. Okay, so we have a gate channel without applying the gate bias. Okay, now the channel is already there. What we can do, we can apply like a opposite gate voltage to turn off the channel. Okay, to remove the inversion charges. Okay, this kind of a device is known as depletion mode MOSFET. The channel is present at 0 gate voltage. And we applied gate voltage to basically turn off the channel. Of course, we need voltage difference between drain and source, then only current can flow. But this is in terms of whether the channel is present at 0 gate voltage, or the channel is present if the gate voltage is more than threshold voltage. Okay. Next, we discussed about different modes of operation for MOSFET. This is important because when we want to apply use a transistor either in an amplification mode, whether we want to use it as an amplifier or whether we want to use it like a simple switch, that depends on the mode, like in which mode we are operating. Okay, so first is the sub-threshold mode. In some books it is also given at, in most of the books it is also given as the cutoff region. Why it is known as the cutoff region? Because for this case our applied gate voltage is less than VT. Okay, so ideally there is no channel, there should not be any current conduction. Okay, so in this case ideally the current conduction is 0. But we can so how it looks, the band diagram, how it looks, if we are applying say no gate voltage, we have a band structure like this, band diagram like this. I am drawing it for NMOS. So we have this source which is N plus. Okay, this is my Fermi level, and it will be similar in case of in the drain side also. So this is source, this is drain. Okay, and this region is P type. Okay, so this is my channel, or the the body region. Okay, so there is this barrier. Electrons from source side cannot go to the drain side. Okay, normally what we do, we apply a positive bias to the drain terminal, and that attracts the whatever the electrons present in the channel, that goes towards the drain side. Okay, now when the threshold voltage is less than Vt, there is no channel. Ideally there should not be any electron flow from the source side to the drain side. But what happens, we know that there may be some electrons which have higher energy. Okay, may be present somewhere here. There will be very less number of electrons, but some electrons may have higher energy to cross this barrier. Okay, so that is why, even though ideally current is not equal to 0, there will be some current. But for practical applications, the MOSFETs are designed in such a way that the threshold, subthreshold current is very less than the current that we have in linear or saturation region. Okay, so this is also known as the cutoff mode. Okay, where current is almost equal to 0. Next is the linear mode of operation. So when VGS is greater than Vt, there will be the channel formation here. Inversion layer will be formed, that is our channel. But if our VDS is 0, then our current will be still 0. Okay, because these electrons here will be just lying around. These electrons will just lie around, but there is no electric field between source and drain, so electrons will not move. I mean, it will move in a random direction. Overall the current will be 0. But if VDS is not equal to 0, and if VDS is small VDS, then we get some current. Okay, and that current is we know the expression, we have learned in the course. I will discuss about it again. We will get some current, and this current actually increases linearly. That is why this mode of operation is known as linear region with VDS. Remember, this is for small VDS value. Okay, now if we have more gate voltage, say this is Vs for some particular gate voltage, and if we have more gate voltage, there will be more number of electrons in the channel, so overall our current will be high. Again, this is in the linear region, and this is say for VGS2, and in this case our VGS2 is greater than VGS1. Okay, so in the linear region, as we can see, there is a linear relation between current and voltage. We can define a linear resistance, which is VDS by ID. Okay. In this region, MOSFET behaves like a resistor. This mode of operation is useful when we want to operate our MOSFET as an amplifier. Okay, we are not discussing circuits in this course, so we are mostly discussing the devices. So the course is semiconductor devices. So if you have done some course on circuits, then you will know that this linear mode of operation is useful when we want to make an amplifier. Now what we do when we want to, how we operate our MOSFET when we want to operate it as a switch. So we use it in the saturation mode. In this case, applied gate voltage is much not applied gate voltage, my VDS is much greater. Okay, very greater. For greater than what value, that we will discuss. Now what happens in this case is that, so we have this, I will not draw the whole MOSFET. This is my N plus regions which are source and drain, and this is my oxide, and this is the metal. Initially there will be some channel like this. Okay, there will be uniform distribution of electrons in the channel. But what will happen when we apply a voltage VDS in the source and across source and drain terminal? Okay, the effective voltage at this point and at this point will be different. So how the voltage varies, how VDS varies, if this is my X and this channel length is say L. Channel length L is a very important parameter in MOSFET. In every expression we will have this. So the voltage drop due to this applied voltage between source and drain terminal will vary from 0 to some voltage VDS. The effective voltage that is responsible to create this channel, that will be whatever the applied gate voltage minus whatever the voltage at this point. Okay. So from the expression we can say that our voltage drop actually decreases towards drain. So our channel, the electron density in the channel will also decrease. A pictorial representation will be like this. When we apply say a small gate voltage, our voltage drop was like this. So because of that we have a channel like this. If we increase our VDS, so what might happen? This drop will be even more in the drain side. So we will have say less effective voltage at that point, and our total channel, the density of electron will decrease towards the drain. Okay. Now at the point where for the voltage drop across drain and source, for which this condition happens, that means the channel is, the density of electrons at the drain end, at this point becomes 0. That point is known as pinch off. So my effectively channel is almost 0 at that point. Now at what point it happens? So it happens when VDS equal to VGS minus VT. In this case and beyond this point, my Q inversion or my channel, the charge density of the channel at the drain end becomes 0. Okay. But from the IV characteristics of MOSFET, we have learned that our VDS versus ID looks like this. Linear in this region when VDS is low, and after this point VGS minus VT, which we call as VD sat, VD saturation, our current become constant. Why this current become constant? What happens? Even though we have, let's say we are taking a point here, so our channel is already, the density is very less, so we are somewhere here, and this is our channel, this is my n plus regions, and this is the oxide, this is the metal layer. Okay, this is my source, this is drain. We are applying VDS which is greater than VDS set. There will be a still constant current flow. Why? Because there will be a very high electric field in this region. Right? We are applying a very high voltage in the drain terminal, there will be a very high electric field. So electrons will still be attracted and this circuit will be like kind of closed. There will be current conduction because of the electric field present in this region. And there will be no increase of current with this, but only that path for electron will be completed. So we get a constant current. Ideally we get a constant current. Actually we don't get a constant current. Okay? So this is the saturation mode of operation where the drain current is constant. Next we will discuss about the IV characteristics of MOSFET. The current expressions were derived in the course, so I will go through it very quickly. So we know that our threshold voltage for MOSFET, the expression is flat band voltage minus QD by COX plus 2 phi F, and this is basically phi ms, whatever the Fermi level difference between metal and semiconductor, and whatever the inversion charges, the fixed and interface charges. Okay, the band bending that happens due to the interface and fixed charges. Now this is at threshold voltage. In threshold voltage we get the inversion. Okay, what happens beyond this threshold voltage? So what happens above threshold? So whatever the gate voltage we apply, that will create the flat band condition, that will create the inversion like 2 phi F, that part, depletion, plus that extra voltage whatever, that will create our more and more inversion charges. Okay, COX. So this is VT plus Q inversion by COX. So what are my inversion charges? Minus COX VG minus VT. Okay. Now how we can get the current? Current I equal to Q by T, right? Charge by time. So this is inversion charge density. Remember, these are everything we are defining. This is like the microfarad or nanofarad per centimeter square. So we have to multiply the area. And what area? The area of the channel. So this is our length L and the width is W. So we will multiply that. So whatever our inversion charges, it's not right. Let's keep it positive. We know the direction how the current flows. So based on that, we can determine whatever the direction. The signs are not important in this case. So Vg minus Vt, the area is W into L divided by tau. So what is tau? Tau, the time that is required for electrons to travel from source to drain. Right? Now what is tau? Tau is the time that an electron takes to travel from source to drain. So this length is L divided by drift velocity of electron. I try to write drift velocity or velocity with this small v because I'm denoting the voltage for the notation for voltage is this capital V. Okay, don't get confused. What is drift velocity? We have learned about this. This is mu into electric field. Right? What is electric field? Mu into whatever the voltage drop divided by the length. Okay, electric field is V by L, right? So this is VDS to L square. So if I put back this expression in ID, so we get the expression for drain current as mu COX W by L VGS minus VT into VDS. Okay. Now this expression is valid for linear region of operation. For saturation region of operation, what is the expression that we will learn. Now how we determine again resistance that is associated with MOSFET in the linear region, that is VDS by ID. So we already know this ID expression, so that linear resistance will be mu CoxW by L VGS minus VT. Okay. The resistance, this is basically like the resistance of the channel, okay, which is like one, so this R linear will be VDS by ID, so this will be mu n Cox W by L VGS minus VT, so this is inverse, right? So if we are applying more gate voltage, the resistance will be less, okay, which we can say like there will be more number of electrons, so the resistance will be less. So this is simply like the expression I equal to Q by T. Okay. Now we can derive the expression for drain current by using something called Gray-Snell approximation. See, this is an approximation. It may not be absolutely correct. Okay, so our ID expressions are not absolutely correct. Those are valid. I mean, the error is very less in certain conditions. Okay, if you remember, we have discussed about the assumptions and approximations in PN junctions. The current expression, we did the derivation in PN junction by assuming certain conditions. We considered that low level injection. We considered that whatever the minority carriers are injected, that reach towards the edge of the depletion region. We have taken assumption that depletion region is completely depleted, right? There are no charges. Of course, those are not correct, like absolutely correct, but that makes our life simple. I mean, the expressions we can derive very easily, and those are valid in most of the cases. Similarly, this gradual channel approximation, this is also valid in certain conditions, mostly in case of long channel MOSFET. If we have a short channel MOSFET, there are certain other non-idealities, those will come. Okay, so what this means, inversion charges, which is Q inversion, changes gradually across the channel. There are many approximations, like there are many assumptions, but I'm writing the important ones. Okay, and our electric field in the X direction, so this is along the channel, is much higher than EY. Across the oxide. What it means, in our device there are two electric fields. One is due to this VDS, whatever VDS we are applying, which is in the X direction we are considering, which is our EX. There is one electric field in the vertical direction as well, because we are applying some gate voltage, so there will be an electric field. We are considering that our electric field that is due to VDS is much higher. EX is much higher, and that is why in this expression you have noticed that I have directly used VDS. If we consider the effect of another electric field, the current may not move as per we are considering. Okay, this is valid for most of the cases, and this is valid mainly for long channel MOSFET. Okay, the electric field, because the length is long, so electric field is VDS by L, so that is much higher. If it is a short channel MOSFET, then it may become comparable, okay, at least for certain VDS values. And next we are considering that we have an ideal oxide, so leakage current is 0 through oxide. So these are some assumptions. There are some other assumptions also, and also carrier mobility is constant. In the channel is constant. If you remember, if this is my electric field and this is my drift velocity, we have a graph like this. We define mu only in this region, right? The slope that gives us the, so mu equal to, Vd equal to mu into E, right? The slope that gives us mobility. But what happens in this region? Our drift velocity saturates, right? We have done few questions on this in earlier sessions. We are not considering all those. We are considering one mobility throughout the channel, okay? We are not considering very high electric field. So in that case, for gradual channel approximation, our expression for this tau will be different, and we will use the effective voltage drop across the channel, that concept. So tau is equal to L by V. The time is equal to distance by velocity, right? This is the normal expression. That's how the electrons also behave. This is L divided by mu into dVx by dx. This is why we are considering dVx by ds, because our actual voltage drop across the channel varies. It is high at the source end, it is low at the drain end, right? This is because as voltage varies, across channel. So Vx, we already know what is Vx. Whatever the voltage drop, whatever the gate voltage that is applied, and whatever the voltage drop at that point of the channel. We can use this tau value in the ID expression and do this integration from 0 to L, okay, because total current is like constant. And if you have already watched the lecture videos, you already know we do the derivation, and that gives us an expression for drain current. That is from this gradual channel approximation. We are considering that our channel density is changing gradually, as I shown in this graph. Like, this is kind of a pictorial depiction of this gradual channel approximation, okay? It may not be like that exactly, okay? Our channel density, the inversion charges, may not vary like this gradually. We get a similar expression, same expression, that is mu cox W by L VGS minus VT into VDS minus VDS square by 2, okay? We will mostly use this expression in our calculations, okay? Now what happens? Ultimately we said that this is our current expression for linear mode of operation. Let's see if this current expression becomes that one if we consider linear mode of operation. And what is the condition for linear mode of operation? For linear mode of operation, our VDS is actually very small, right? If VDS is small, say 50 millivolt, 50 into 10 to the power minus 3 square of that will be even smaller, right? Something into 10 to the power minus 3 square. So we can actually neglect this portion. So our ID becomes the expression that we got earlier. So this is mu COX W by L VGS minus VT into VDS. Okay, like this. What happens in saturation? We said that after the point of saturation, our current does not increase, current is constant. And what is the point of saturation? When our VDS is equal to VGS minus VT. Right? If we use this saturation, the VD side value in this expression, we will get ID as ID set. This is constant. This is constant, that it does not vary with respect to VDS. It may vary with VGS, gate voltage, it may vary. Mu into COX, W, VGS minus VT by 2. So this 2 is different, remember this. Here we also define a parameter called transconductance. Which is mu COX W by L. Remember what is transconductance? What is conductance? This is the opposite of resistance, right? And what transconductance means, in general, what is we will define transfer characteristics of MOSFET and output characteristics of MOSFET. What is normally that this trans portion means? It is that we are taking one from one side, input side, and one parameter from output side. In this case, we are taking input side is our what? The gate voltage, that is what we are applying. So VGS is our input. And what is our output? ID, right? And how we define conductance? It is the opposite of resistance, right? Resistance is voltage by current, right? So conductance is ID by VGS. It will be something like that. And because there may be a variation of there may be a change of ID due to VGS, so we define this as like del ID by del VGS. If you do del ID by del VGS, we will get this expression for transconductance. Okay. Now very briefly I will say, I'll just only say this. We have mentioned that when our after pinch off, actually I'll explain very briefly. Okay, after pinch off we have like a constant current, okay, because there will be this electric field, but actually that current actually changes because our overall this density is changing. Q inversion is changing. So ideally, even though it is a constant current, but practically we get a bit of more current than this. This is known as channel length modulation. If this is in the curriculum for the next week, then we will discuss in detail in the next week also. Another non-ideality, we are discussing about this ideal conditions of MOSFET, mainly long channel MOSFET. But we are also considering that in all of these cases, we are not applying any bias to the body terminal. we are basically shorting our source and body. Okay, why we are doing that again? We want to make this n plus p and n plus p regions reverse bias all the time. But what we can do, we can apply a negative bias to the body terminal also if it is a NMOS. Then source is already 0 at 0 voltage. If we are applying a negative bias, so this is P silicon, so this will be still in reverse bias. But that actually affects the threshold voltage. And what is the effect of that threshold voltage due to this body bias effect? This was not derived. I will also directly write the expression for that. Because of that body bias, we are applying a negative voltage that will obviously change the channel dynamics. Okay. Now our see what will happen. We are applying a negative voltage here, right, in the body terminal. We are basically repelling the electrons from this side towards this side. Okay, so basically we are helping in creating the channel if we apply a negative voltage to the body terminal, right? So our effective threshold voltage will actually decrease. So how much decrease? After the derivation it comes like this. Yeah, whether it will decrease or increase, that depends on the PMOS or NMOS. So VBS is this. So what will be this value for NMOS NMOSFET? So this body that is in negative, so this value will also be negative, so this is positive. Okay, this minus. Just give me a second, okay? Oh, actually the threshold voltage actually increases, because when we apply a negative to the body terminal, so our what will happen, this was our initially our band diagram used to look like this. Okay, so this is source, this is drain. When we apply negative voltage, that means our this will go up, right? We are applying negative voltage, so our bands will shift upward because there will be more number of electrons. So our threshold voltage will actually increase, so this barrier will increase. Okay, so this happens, and because of that actually threshold voltage also increases. Okay? That is why this term. Remember, you have to be careful with the sign of this body bias, because VBS, that is negative for NMOS transistors, okay, NMOSFET, because we want to keep our N plus P, or that junction between body and the source and drain, that is reverse bias. So we will always apply the body or the bulk potential that is lower than the element that is more negative than the source terminal. very briefly we also discussed about how these are used in circuits, especially for digital applications. So maybe you are already familiar with the circuit symbols for NMOS and PMOS. So this is for NMOS circuit symbol. There are few more also, and this is for PMOS. This is the gate terminal. Now few parameters, those were defined. First one is input resistance. So what is a MOSFET? MOSFET is a voltage controlled current device, right? Why it is a voltage controlled current device? What is the control voltage we have? We have the control voltage as the gate voltage. With that we either turn off the channel or on the channel. Okay, so it is voltage control. Why it is a current device? Because our output is the drain current. Okay, you must have studied about this different sources: voltage controlled current source, current controlled current source, and for all of these the input and output resistance is important. So what is a MOSFET? MOSFET is a voltage controlled current source. So we are discussing about input resistance. I mean that side where we apply the gate voltage. Ideally, what should be the resistance of that? Ideally, the input resistance of a voltage controlled current source or voltage source, that does not matter. For a voltage controlled source, the input resistance is very high, so that it can take that voltage drop. Okay. (10 to the power 9 minus 10 to the power 12). And what will happen if the input resistance is very low? Then that terminal will start to draw current, right? If the resistance is low, then the current will pass through. But we know that there is no current conduction between the gate and the channel because of there is an insulating layer. The insulating layer, we consider it as ideal, or it is closed to ideal. There is no current conduction between that. So that means there is a very high resistance. There is no current conduction. We only want that voltage drop. Okay, there is no current. We ideally don't want any current conduction. That is why the input resistance will be very high. Okay, that is because of the oxide layer. What happens? What is the output resistance? If it is a voltage controlled current source or current controlled current source, the output resistance should be low. Why? Because that output terminal should not draw any current. If you remember, there is like these two resistors, right? If this resistor corresponds to the output terminal, and this is the resistor we are connecting to collect that current, whatever the output current, for this case say ID, our drain current. We don't want the output terminal to draw that current. Okay, we want that output current to pass through this. I'm sorry, this is opposite. Okay, we want the current for what happens for current source. Just give me a minute. Okay, for current source we want that it can flow current, right? So for current source we want ideally a low output resistance. initially I was right. Sorry for this confusion. Okay. So ideally for a current source, we don't want the source itself to draw current. Okay. So the output resistance we want to be high. Let me just verify. I have studied all these things, but I don't remember very clearly. Both the input and output resistance should be high, because we don't want any current to flow through the input side, and we want all the current to flow through the output terminal. The device itself should not draw current. Okay, that is what the high output resistance means. Okay, if this is our device, it should not, the resistance of this device should be very high in the output side, so that there is no current through this, but it can deliver current. So the device can deliver current. So output resistance of a current source, that should be very high. I think you have studied this in analog circuits, some courses. I don't know the background of all of you. How we define it? We denote it with R naught. This is dVds by dId. Okay, and this is at a constant VGS. So this is constant in linear region, because we get a constant slope. And in saturation, even if we increase VDS very large value, current does not increase much. So our ideally that change is 0, dId is 0. So we get a large output resistance. This is the behavior of a ideal current source. Okay. There are other few terms that we discussed: drain and transconductance. Okay. So transconductance is denoted this term, so which is dId by dVGS. This is at a constant VDS. Okay, I have already discussed why we call it a transconductance. What is conductance? Why we call it transconductance? Because we are taking one from input side, one from output side, and this is mu COX W by L VDS in the linear region, and mu COX W by L VGS minus VT in saturation. Drain conductance GD, it is denoted by ZD, which is the inverse of this. So this is basically inverse of dId by dVDS by dId. So that is the resistance of conductance is like opposite. Okay. When we use MOSFET as a switch, we either operate in cutoff region or subthreshold region, or in saturation region. Okay. When we want to use it as an amplifier, we use it in a linear region. And when we want to use it as a switch, ideally we want that whatever our ID of, that is in the cutoff region, that is very very less. Okay, so we have also defined another term that is known as subthreshold swing. This is very important term in MOSFET. How it comes, that was discussed in the lecture video, please go through it. This is the amount of voltage that is required to produce one order change in drain current. From where we get the 60 millivolt per decade, that value, the typical value of subthreshold swing. Okay, basically what happens when we have this barrier, this current electron, how it can crosses, this is what we call as thermionic emission, and that depends on temperature, and that is why the 60 millivolt per decade, that constant number comes. Okay, it may vary slightly. I mean, there is this n into 60 millivolt per decade, so this n value can be in between 1 to 1.5 based on the technology, but it is almost constant because it depends on the temperature. Now it was briefly discussed about in the class how we can use NMOS and PMOS and create a CMOS circuit. The CMOS inverter was discussed. So how a CMOS inverter looks like. We have the PMOS here, we have the NMOS below. This is the source terminal of the PMOS, which is connected to VDD. VDD, that is the higher voltage, and the source terminal of the drain is connected to the ground. Okay, we apply some input voltage and we get an output voltage which is the opposite. Why? Basically what happens when we apply a 0 volt, okay, so 0 volt, which is like so this NMOS will be off. So now this point is basically connected, NMOS will be off, this PMOS will be on. Okay, so basically this path is on, so my output will be 1, which is VDD. When this value is 1 or it is equal to VDD, logic 1, that means equal to VDD, so my NMOS will be on because it is higher than the threshold voltage, but this will be off. Okay, because that is not less than the threshold voltage, right? For PMOS the threshold voltage is negative. When it is off, basically this path will be open, like to this ground path, so we will get 0 output voltage. So that is the inverting action. Okay, and why the CMOS technology is very powerful, and there is so much improvement in this technology, because as I told earlier also, the power consumption is very less. At a time only one transistor is on, one MOSFET is on, so there is no direct path between VDD and this drain terminal. So overall the voltage drop is very low. There is no leakage, there will be some leakage current maybe, but overall the voltage drop is very low. Power dissipation is very less. Okay, so let's go to the questions. So this graph is given in the first question. The output characteristics of a NMOS is given in the figure. Identify the modes of operations. In the regions A, B and C. Options are subthreshold, saturation, linear, option C is subthreshold, linear, saturation, B is so what is the answer? C. In A, ID is 0, so that is subthreshold. B is the linear region and C is the saturation region. In a MOSFET operating in saturation regime, channel length modulation effect causes what dash. So the options are N increase in the gate source capacitance, a decrease in the output resistance, a decrease in transconductance, a decrease in the unity gain cutoff frequency. So this term we have not discussed, so this is a circuit terms and not discussed much. Okay. So what is the answer? I have briefly discussed about channel length modulation. So discuss that, as even though we are considering our ID is constant, but actually it is not constant, it increases slightly. What is the answer? So what is channel length modulation? We have this picture, right? This picture is not exactly correct, but for our understanding this is very useful. This is my metal gate, this is source, this is drain, and we are drawing our channel like this. This is my channel, there are electrons, electrons, electrons. This is a p-type silicon, right? Our channel is of this type. So this is the point where the pinch off happens, and that is VDS set we are defining, which is our VGS minus VT. And what is our current expression? ID is equal to, considering gradual channel approximation, COX W VGS minus VT into VDS minus VDS square by 2. Okay, and we know that in ID set we have this expression mu COX W by actually twice L VGS minus VT. What happens when we apply more VDS than this VD set? I told that our channel becomes like this, and how this current still flows because of this high electric field in this region. But what is happening to our channel length? This was our channel length L initially. Now there is a change in channel length, right? The channel length actually decreases. So because of that our current actually increases. I mean, this is not directly straightforward, but from this picture you can see that our channel length decreases, so overall our current increases. So there is a slight increase in the current because of that. Okay. So our graph, ideally what it used to look like this. Now there will be a slight increase. What is the output resistance R0 we are defining? This is the VDS by ID, right? DID. We are saying that because there is no change in our drain current, so our output resistance was very high in the saturation region. But you can now see that there is a slight slope. So this is non-zero, and there is a slight slope, and because of that what will happen? Our R0 will actually decrease. Okay, this slope, you consider this slope and this slope. So this is the effect of channel length modulation, because our channel is actually decreasing. Okay. So the answer is this B. There is a decrease in output resistance. That is the effect of this, because the drain current slightly increases after this point. Okay. Now if our channel is very long, this delta L that is happening, that is not very significant, so we can neglect it. We can say that which is our almost same as the ideal condition. But even if our channel length itself is very small, then our delta L change, that will be very significant, and that is why it is more important in short channel MOSFETs. Okay? I hope it is clear. we have to calculate the drain current. This value is given, transconductance parameter, and VGS and VDS is given. So we have to calculate ID in milliampere. So the options are 0.28, 4.5, 2.5, 5.1. What is transconductance parameter? This mu COX W by N. So we know that our expressions for ID is mu COX W by L, VGS minus VT into VDS minus VDS square by 2. This is for linear regime. We can neglect this term also if our VDS is very small. And in saturation we have this expression W by L 2L VGS minus VT. Oh, it is actually square. I have written it. Okay, if I make this kind of a mistake, then you please tell me. This is square. This will be VGS minus VT square by half, so there will be this 2 and this is square. This is for saturation region. I'm not feeling very well and so I'm making this mistake. So if I make this kind of a mistake, then please tell me. So I have this ID expressions. Now which expression I have to use? For that I should check whether the device is in linear region or in saturation region. Okay. So this is mu COX W by L, that value is given 1 milliampere per volt square. Okay. So threshold voltage is given, so VGS minus VT is what? VTH, right? Because VGS is 2 VTH, which is 0.75. And our VDS is 1 volt. So VDS is actually greater than VG minus VT, right? So that our device is in saturation. So we'll use this expression. So our ID will be 1 milliampere per volt square. VGS minus VT is 0.75 square. Okay. What is the value? Oh, this is by 2, right? There will be this 2 term. Yeah. That is the only place where you should be careful. This is 0.28 milliampere, because this will be also volt square, so when your answer is in milliampere. So the correct answer is A. I hope this is clear. I hope that I have not made any more mistakes. If you can point out. If I have made any, then please let me know. Okay, let's go to the next question. You know what is pinch off? You already know this. This is the point where the inversion charge density near the drain end is 0. Okay, so I try to draw the figure as per that. The drawing may not be perfect. This is n plus. This is my channel. This is oxide, this is gate. The source is grounded. This is VDS, this is VGS. I have this depletion layer because this N plus NP substrate and this N plus NP substrate is in reverse bias. So my figure is given like this. So the options are the conditions, what condition it indicates. VDS less than VGS minus VTH. Option B is VDS equal to VGS equal to VTH. Is VDS equal to VGS minus VTH. VDS VGS minus VTH. So this figure is slightly not correct. It is saying that this is onset of pinch off. Okay. So what is the condition? We already know this. So it is the correct answer. The question is onset of pinch off. Okay. The channel becomes 0 here. So the correct condition for that is VDS is equal to VGS minus VTH. Okay. In that case, our inversion charge will be 0 at that point. Next question is, For short channel and MOSFET, that means our L is not very large. With p-type silicon substrate, the critical field at which electron saturation occurs is around 1.5 volt per micrometer, and saturation velocity approximately 10 to the power 5 meter per second. Based on the figure below, velocity saturation effect, choose the incorrect statement. Okay. The velocity of carriers tends to saturate due to scattering. There are few concepts in this question, so that's why I want to do this. Velocity saturation effects are less pronounced in PMOS. The graph that is given Okay, I'll draw it. Electric field in this direction. So in this axis, voltage per micrometer, say, and this is drift velocity, which is meter per second. And the graph typically looks like this. The critical electric field for which this velocity saturation happens, this is 1.5. okay, and this is our saturation velocity. The value is given 10 to the power 5 meter per second. That is the typical value. Now what I want to discuss here is that this is the typical behavior how electrons behave under electric field inside the semiconductor. So we know that our drift velocity is proportional to electric field. This is again for small electric field. We are applying some electric field. Electrons will move because of that electric field towards the positive terminal, right? If we apply more electric field, the electrons will move faster. So that means our drift velocity of electron is directly proportional to the applied electric field. Okay, this was we discussed earlier, and this proportionality constant we were saying as mobility, mu, right? Similar thing that happens if we are considering a p-type substrate, p-type semiconductor. Then the drift velocity is the the mu is the mobility of holes, right? Now this condition is true, this statement is true for low electric field, less value of electric field. What happens when the electric field is very high? So electrons try to move in a very fast speed, and there will be a lot of scattering with other electrons, with other interfaces. So overall the velocity of the electrons or holes will be saturated. There is nothing like if we increase the electric field, the velocity will keep on increase. Because of the scattering effect, we will have a constant constant drift velocity if our electric field is very high. Again, what is scattering? Electrons may collide with one another. That is one type of scattering. It may collide with the different atoms of the lattice. I mean, it cannot directly collide, but there may be a deflection of the path. Okay, it may collide near the interface. The scattering effect will be even more. So because of all of this scattering effect, we get an average drift velocity which is like constant. Okay, so this is the typical drift velocity versus electric field graph. This graph is linear in the low electric field region, and from the slope we get the mobility. There is no concept of mobility after this critical electric field point. So this is our EC, critical electric field. Okay, beyond this point we have a constant drift velocity. There is no concept of mobility, right? Why we are discussing it in terms of short channels in NMOS? In short channel, our channel length will be very small, right? What is this electric field? This is the drop due to VDS. What is electric field? Is V by L, right? The definition of electric field, the basic formula is V by L. This is the applied voltage across the length. If our length is very small, that electric field will be very high. So in short channels, if our channel length is very small, there may this condition may arise that our electric field is such that it reaches the critical electric field or it is nearby. In that case, we cannot define mobility. We cannot use the expressions that we have used earlier. Okay, there will be a constant drift velocity VD set, which is 10 to the power 5 meter per second. This is the typical value for semiconductor, in the range of 10 to the power 5. If you are given a question where you are trying to calculate drift velocity and if you are finding a value like 10 to the power 10, 10 to the power 12 meter per second, you should immediately think that no, this is not possible. Like in semiconductors, this value is 10 to the power 5 meter per second or close to that. I mean maximum that. Okay, cannot be much higher than this value. So what we were discussing in short channel MOSFET. In short channel MOSFET, this condition may arise very quickly. In long channels, we are not bothered about this velocity saturation effect. Okay, so this is known as the velocity saturation effect. That is why, like many of this, as I told earlier also, all these approximations, all the assumptions are true only at certain conditions. All the equations that we are deriving, that is true if our assumptions are correct or close to correct. I mean, the error is, if the error is not that much. Okay, yeah. So for expressions will be different, or the situation will be like the whole behavior will be different for short channel MOSFET. So what is the incorrect statement out of this? So as I told that the slope of the region, the statement B, the slope of the region before reaching the critical field represents the carrier mobility. So this gives, I mean, dVd by d electric field, that gives our mobility, right? So this is true. The velocity of carriers tends to saturate due to scattering effect, that is also true. Okay, there will be some average saturation velocity after the critical electric field point. Velocity saturation effects are less pronounced in PMOS. This statement is also true. Why it is true? See, the slope that denotes the mobility, right? We know that the mobility for electrons is much higher compared to mobility of holes. The typical value for silicon mu n is around 1300 centimeter square per volt second, right? For holes it is around 500, 480. Okay, so this value is small, so the slope is also less. If we are considering the similar electric field, so the critical electric field will be much higher in that case. Okay, so this effect is less prominent in PMOS because of that. You got my point? Like it will be like this kind of a behavior. Why it does not work? Okay, in case of PMOS. So B, C and D are true. For lower field, carrier mobility is not constant, so obviously this is not true. So our incorrect statement is A. So our answer is A. I hope this is clear, the velocity saturation effect and why it is more prominent in short channel MOSFET and particularly for N MOSFET. Let's go to the next question. D point repeat. Okay. So velocity saturation effects are less pronounced in PMOS. What is the typical value for mobility in case of electrons in silicon? Around 1300, right? We have done calculations using these values. For holes it is around 500. So mu n for, I mean, most of the cases the mobility of electron is actually higher than the mobility of holes. Okay, what is mobility? Basically the slope in this linear region, right? If the slope is more, mobility is more. So if this given graph is say for NMOS, this is given for NMOS, for PMOS the graph will be, because the mobility is less, so the slope will be also less. So the graph will look like this. In this case, the critical electric field is at this point, so it is much higher than the critical electric field for NMOS. Okay, the slope will increase very less. Okay, so we will not reach critical electric field. That is why we will not reach velocity saturation. So for example, at this point, electric field point, NMOS will be in the for the electrons will be in the V set, that is the maximum velocity it can take. But for PMOS, we can still use this mu into electric field, that expression, because it has not reached yet the saturation. Okay, so that is why in case of PMOS, we this is not very prominent, the velocity saturation effect, because within the range of electric field that we mostly operate, I mean, it does not reaches the velocity saturation point. We need much higher electric field in case of PMOS to reach velocity saturation. Okay. This slope, this denotes mu n. This slope denotes mu p. I hope it is clear now. Okay. What is the main function of P-channel MOSFET in CMOS inverter circuit? To pull the output to ground when input is high, V is what it means. Option C is to pull the output to VDD when the input is low. Option D is invert the signal. So what is the answer for this? We have the CMOS inverter circuit. We have one PMOS, that is the symbol for PMOS. This is the source terminal which is connected to VDD. In case of PMOS, we connect it to the highest voltage. Okay. In case of NMOS, we connect it to ground. Source is ground, right? So this is my source here, this is my source here. This is the drain terminal which are connected. This is my input voltage where we apply the input voltage, and this is my output voltage. I may have a resistor or a capacitor here, okay, to draw the current or to charge or discharge. So when the PMOS will be on, so for PMOS it will be on when Vin is less than Vt, right? Vt is negative, say say -1 volt, okay. Let's write a more term, okay, that's much more convenient. VGS is less than VT, right? Say we are applying, so say this VDD is 5 volts, okay, and we are applying 0 volt initially as input voltage. So this is the gate terminal, right? So what will be VGS? This is 0 minus 5, right? So PMOS will be on in this case when Vin is 0 volt, VGS, this is for PMOS, this will be 0, this is 0 minus 5, 0 minus 5, so minus 5 volt, which is less than VT. Typically VT is around minus 1 volt, minus 0.7 volt, like that. So PMOS will be on. When PMOS is on, basically this path is on. There is a connection, there is like this channel or the path between the source and drain, and our output terminal is connected to this drain, right? So basically this path will be on. So our output will be 5 volt, which is logic 1, okay, or digitally 5 volt we say as 1, right? So we are applying 0 input voltage, but we are getting 5 volt of output voltage, or logic 1 as output voltage. That is basically the inverting application. So what PMOS is actually doing? PMOS is connecting the output to VDD. That is why PMOS is known as pull-up transistor. Okay, it pulls the output terminal to the higher value, the VDD. What happens if NMOS is on? If our applied voltage is say 5 volt, then VGS will be 5 volt for this NMOS, which will be higher than the threshold voltage of for NMOS. So this is on. PMOS will be off. Why PMOS will be off? So 5 minus, so that is 0 volt. VGS is 0 for PMOS, and so this condition is not satisfied. So PMOS will be off in that case if our input voltage is high, right? But NMOS will be on, and this path will be on in that case, and our output voltage will be 0 volt in that case. So the NMOS actually connects the output voltage to the ground terminal through the source, okay. So it pulls down the output towards 0 voltage, and PMOS pulls up the output voltage to the higher voltage value, that is VDD. So PMOS is pull up transistor, NMOS is pull down transistor. So what is our correct answer? Our answer is C. PMOS is used to pull the output to VDD when the input is low. This will be discussed in more detail if you take some circuits course. This is not a circuit course, so just trying to give you an overview this time. Let's do it quickly. So this was a gate question. An NMOS transistor is operating in linear region, has ID of 5 microampere at VDS of 0.1 volt, keeping VGS is constant, VDS is increased to 1.5 volt. given that W mu n cox by L is 50 microampere per volt square, then the transconductance at the new operating point so in terms of we have to calculate microampere per volt. Okay, what is the value? So let's do it quickly. So initially when it is in linear region, we were given that what is the expression for ID? ID is given to us mu n cox W by L VGS minus VT into VDS minus VDS square by 2. Okay, and this is given to us as 5 microampere, and this portion is given to us as 50 microampere per volt square. VDS is given to us, which is 0.1. Initially it is 0.1. So we will calculate VGS minus VT, because for the next part also our VGS is constant, VT is threshold voltage is already constant. So what will be this value? Let's calculate quickly. So 5 by 50 plus so this is 1.05 volt. My now VDS new, that is 1.5 volt. So this is actually greater than VGS minus VT, right? So this will be in saturation. At new operating point, my device will be in saturation. Why this is important? We have to calculate transconductance. If you remember what is transconductance, the expressions are different for linear regime and saturation regime, right? So transconductance is del ID by del VGS at a constant VDS, and these are the two expressions. Okay, so our value will be, because our ID expression is different, so del ID by del value, so GM will be mu n cox W by L. You should remember this expression, transconductance expression for linear regime and saturation regime. Okay. So this is given as 50 microampere per volt square, and this we have calculated as 1.05. Don't multiply VDS value in the expression, your final answer will not be correct in this case. The only important point here to check whether the device is in saturation or linear, because it is explicitly written that initially it is in linear region, but after that when we increase VDS to 1.5, whether the device is in linear or saturation, that we don't know. This is the only part where you have to be careful, otherwise this is simple calculation. Okay, so this will be 52.5 microampere per watt. This was a question and gate 2024. So it's already time. If you have any quick question, then you can ask. Otherwise, I will stop the session here. Okay, let's stop the session here. I hope the session was useful. Thank you for attending the session. Let's meet in the next week.